This is Jack Jackson. Today we're going to talk about hypothesis testing and some confidence intervals for two samples, and we're going to look at the differences in the means from those two samples. So primarily we're going to be talking about a two-sample t-test here. Now, recall that we'd earlier talked about both the z-test and a z-interval, and also a t-test and a t-interval, from where we were having a one-sample situation. In those situations we had one sample, we were computing the mean of that sample, and we were comparing that against some population which we knew the hypothesized mean of that known population. In this case, we do not have a known population to compare against. What we have is we have two samples, and we want to compare the means between these two samples and to see if there's a difference. So first of all, we're going to look at what if your two samples are dependent and we have paired differences. So for example, before and after measurements. Now this particular situation is probably one of the most common and useful situations that we can work with. Many times, if you want to find out if something is going to have some effect, you perform an experiment. You do a pre-test and a post-test. You test before the treatment, whatever it is. You apply that treatment, and then you test afterwards. This can be used in many fields. And this is, if you can control for the other variables, this will give you very strong evidence that what you're doing is making some difference, if in fact it is. But this really is not a two-sample situation. What it is, it's one sample of ordered pairs. And so what we end up doing is we take our set of ordered pairs and we subtract the coordinates so that we get basically after minus before and compute those differences. Then we have really just one sample, and we treat this just like a one-sample t-test or z-test as appropriate. By doing after minus before, positive value would mean an increase, and a negative value would be a decrease, and of course a zero would be no difference. And we treat this as a one sample, so we use a one sample z-test if the population standard deviation is known, or much more commonly, we would use a one-sample t-test if the population standard deviation is unknown. So let's look at an example. In USA Today, on September 17, 2009, a Bloomberg News poll was quoted at finding that Americans were planning on keeping the spending down, and because the economy wasn't doing great at that time. So suppose a group of 15 households noted their household spending in March, and then noted their household spending 6 months later in September. The mean of the paired differences in spending was calculated to be a drop of $75.50, negative $75.50, and the standard deviation was 66.20. Does this sample give sufficient evidence of decreased spending at the alpha equal 0.05 level? And what's a 95% confidence interval for the change in monthly spending? So now we're going to do both the confidence level and hypothesis testing. See if you can go ahead and do this now. Press pause. Well, notice that we're testing the population standard deviation is unknown. This standard deviation is from the sample. So this is a t-test. It is a one-sample t-test because we have before and after data. And basically, we do the differences there. So basically, every family recorded their spending in March, their spending in September. Then they did September spending minus March's spending. And basically, that's the numbers that we looked at. We have a sample of those. Okay, and there were 15 of those families. So we have those 15 differences. And somebody's already computed the summary statistics for us. And they found the mean and standard deviation from those 15 differences. So the null hypothesis is that there's no difference in change, no change, which is no difference, or a mean change of 0. That's the null hypothesis. And the alternative hypothesis is the mean change is less than 0, that there's actually been a drop in spending. Well, we just do this on a calculator. We do our since this is all nicely built in, it's pretty easy to do on the calculator. So we just do a t-test, a one-sample t-test, or just called a t-test in your calculator. So you just go to your calculator, say if it's a TI-84, and you go to Statistics, left arrow once will put you on Test, and go down to T-Test, which is about the second or third one down there. Choose it. And in this case, we have summary statistics, so we set this on stats for input on stats. The null hypothesis is that the mean is 0, no change. The sample mean is negative 75.5, so it dropped that much. Standard deviation that we got from our sample was 66.2, sample size of 15, and we're going to test that the true mean is less than the 0 that was reported. So then click on Calculate or Draw. Here I did Calculate. And so the t statistic is negative 4.4, a p-value of 2.9 times 10 to the negative 4. So that's 0.00029. And so since that is less than the alpha of 0.05, we reject the null hypothesis in favor of the alternative hypothesis. So at that p-value, there is sufficient evidence to conclude that Americans average less household spending in September than in March of 2009. Now, what is a 95% confidence interval for this mean change? Well, now go back to your calculator and do Stat, go to Test, and go down to, you may have to scroll down, but go down to T-interval. Now when you pull this up and say stats, since you just entered this information, a lot of it's going to be entered in for you already, so you don't have to change it. In fact, these first three numbers will be the same. You may have to change the confidence level to 0.95, and then just click on Calculate down here at the bottom, and it returns our confidence interval and our summary statistics, which actually we typed in. So a confidence interval there of 95% confidence interval is $112.20. Drop up to a 38.84 drop. So the true mean, we're 95% confident it's somewhere between these two values. So again, this is really nothing new here. This is already really a one sample situation. You just find the differences first and then do that. Let's do another example like this. So 10 subjects with borderline high cholesterol levels were randomly recruited for a study that involved taking a nutrition education class. Cholesterol readings were taken right before the class and then 3 months after the class. And we're going to see if that's made any difference. And so the following table gives the results. So we have subjects 1 through 10. We have pre-test and post-test data. Now notice, just pre-test and post-test data by itself doesn't make it dependent, but the fact that these are the same subjects, then this is definitely dependent. So, we'd expect subject 1 to have a pre-test and post-test that are very kind of similar, but it might be very different than subject, say, 7. But of course, if with this class is working, what we hope is that all of the people are going to go down, or at least most of them, or on average, they're going to go down. So we want to determine if this data that we have here is sufficient evidence to support the conclusion that the class helped lower cholesterol levels. And we're going to use an alpha equal 0.05 level. And then we're going to also go ahead and do a confidence interval as well, a 95% confidence interval for the mean change. Again, this is dependent samples. See if you can go ahead and figure this out on your own. Press pause now. Well, the first thing we want to do is compute the differences. Now, to do this, it's very easy. I've got them actually worked out here. I could do these all individually by in my head or on paper or in a calculator. But I can also do this all in a calculator pretty easily. Go to your calculator and hit Stat and then select the first thing that's Edit. Put your cursor on L1 and hit Clear, Enter. Put it on L2, Clear, Enter. L3, Clear, Enter. And then enter all of these values here. For L1 is the pre-test, L2 is the post-test, and I'm making sure that I line them up so that the first line is the first subject, the second line is the second subject. Now to get L3, put your cursor on L3, right up here at the top, and then press L2 minus L1, enter. L2 is second 2, subtract, easy. L1 is second 1, and hit enter, and it will automatically compute all these differences. Now then what we're going to do is we're going to do a one sample t-test on L3. So then we just go to our test, t-test. This time it's from data, not summary statistics, so we select data. It's going to ask us what our null hypothesis is. Again, the null hypothesis is that this class didn't do any good, that there would be a zero change. So the mu naught is 0. Our list of data is the list of differences from L3, all the way frequency 1, and we want to test for the true mean being less than 0, so a negative indicates a change. Now just a quick look at the data, at the differences. If you notice, they're all negative except for one, so only one subject had an increase in cholesterol level. All of the others at least had some decrease. So it looks like that's probably going to be enough to make a significant difference, but let's go ahead and do the t-test, get an idea of how significant we got on the p level there too. So then we calculate that, and notice it comes back with a t-test statistic, negative 3.39, and then also a p-value, 0.00397. It also comes back with x bar, negative 26.3, so that's the average of all these differences. If I typed in all these differences in and just average those, that would be the x bar. And the standard deviation of those differences, sample standard deviation is about 24.5. And the n is 10, so there are 10 data values. So, what do we see for a p-value? Well, we got a p-value of 0.004, roughly. Well, that's definitely less than 0.05, so we reject the null hypothesis, and we conclude that, in fact, there was a significant drop in cholesterol level. Now, the only problem with a study like this is controlling for extraneous variables. If the only thing that was different before and after was what they learned in the education class, then we could pretty clearly say that the education class caused this. But what we do know for sure is that there is a strong difference here, that there's a statistically significant difference. We don't know for sure that it was the class that caused it, but if we can reasonably control for other variables, then we can make a good case that that's what happened. Now if we want a t-interval for the confidence interval for how much did they lose, so far we just said that they lost some. We want to try to figure out what the average change was. Of course, the average difference is negative 26.3, so on average they lost 26.3 pounds, or not pounds, this is a cholesterol level, 26.3 in their cholesterol rating. Okay, but what about a confidence interval for that? Well, we just do a t-interval, one sample t-interval, and the input is from data again. Our list is list 3, frequency is 1, confidence level is 0.95, and calculate. We're 95% sure that the true mean change caused by this class, if we're confident that this is the only main factor, is about 44, a drop of between, say, about 8.8 and 43.8. So far, two dependent samples, before and after data especially. This is just paired differences. This is really a one sample situation. You just take the two before and after data, subtract, which is what got list 3 here, and use that to make your differences. Let me pull up the calculator for just a second. and take a look at this. So if you go to Stat, Edit, I have some different data in here, but I don't want to type in all this data again. But I have some data in here. So just to show you how to do this, if I've got something else in list 3, I can go up to list 3, put your cursor on the L3, hit clear and enter, and that will clear that out. So you want to clear that out. Now for the data that I have here, may or may not be appropriate for this, but let's say we want to do paired differences. We could do L2 minus L1. So if L2 was after data and L1 was before data, this is going to compute the changes. And so that's how we got those things. And then if we went to Stat, Tests, and we chose what we needed, and it was a one sample t-test or just a t-test, like this, and we worked from there. Okay, and that's from there, then you kind of got the screens that you see down here if I put in this actual data. Now let's take a look at a situation where we truly have two samples, two independent samples. So if we assume that we have data measured from two independent samples and they are potentially different populations, we'll use subscripts to identify parameters for each sample. So for example, n sub 1 means the sample size for data set 1. N sub 2, sample size for data set 2. Mu sub 1, hypothesized mean of the first data set. Mu sub 2, hypothesized mean, or the true mean actually, of the second data set. X bar sub 1, the sample mean of the first data set, and so forth. Sigma sub 1, the sample standard deviation of data set 1, and so forth. So it turns out if both populations are normally distributed, then the difference in sample means will also be distributed normally. And so we'll call D the difference in those sample means. So D is X bar, actually I'm going to do this, X bar 1 minus X bar 2. Okay? And mu of the differences is X bar 1 minus X bar 2. I originally had it this way to agree with the paired differences, but I think we're going to change it because I think your calculator does it the other direction. And then it turns out that the standard deviation is of the differences turns out to be you take the variance of the first sample divided by this, the sample size, plus the variance of the second sample divided by the sample size, and then take a square root. That turns out to be the standard deviation of the differences. We're not going to go over how that's derived, but we'll just take that as a fact. Well, most of the time we have two independent samples. If we know the population standard deviations, then we can use the formulas on the previous slide and actually use a two-sample z-test. But in reality, we almost never know the population standard deviation. So we're going to use a two-sample t-test, and we're going to use a non-pooled version of that. And this is basically what you get. So the difference here, again, now I've got it in the order that your calculator does it. X bar 1 minus X bar 2 is the difference. The mean, that's the difference in the sample mean. So in other words, you take the mean of each of the two samples first. They don't have to be the same size, but just take the means individually and then subtract them. Notice it's a little different than what we did in the paired differences. In the paired differences, we took the differences first, then we found the mean of the differences. Here we find the difference of the means. And so then we look at the mu sub D is the difference in the actual means of the populations, mu 1 minus mu 2. And mu sub D is what we really want to get our hands on, but that's unknown, so we find just D, the difference in the sample means. Now, we're going to use this formula for the standard deviation of the differences, and that is S sub 1 square over n1 plus S sub 2 square over n2, and then take the square root. Notice that that is basically the same formula that we had for the variances, for the standard deviation in the z-test, but I've replaced sigmas by s's. Okay, so this is the population, not population data, but sample data. So we take our sample standard deviation, square it, and divide by the sample size for this first sample. Do the same for the second sample, add those two together, and square root. That turns out to be our standard deviation of our differences, sample differences. Now, as you know, when you're dealing with a sample and finding a t-test, the sample size is going to determine the degrees of freedom. Now, it was pretty straightforward and easy to figure out the degrees of freedom whenever we were dealing with one sample. It was just the sample size minus 1 was the degree of freedom. It turns out there's a more complicated formula here. That's the non-pooled version of the degrees of freedom, and we use this to find the appropriate degrees of freedom. And if you look, it's the numerator here of this is the same thing as the s sub d without the square root, but then you actually square it. So s sub 1 square over n1 plus s sub 2 square over n2, whole quantity squared. The denominator is s1 square over n1, then square that divided by n1 minus 1, plus the other one's s sub 2 square over n2, square that whole thing, divide by n2 minus 1. Add these two things together, and that's the denominator. So, okay, kind of a complicated formula. Good news is you're not going to have to memorize that or even apply it directly. What's going to happen is when you do, luckily there is a 2-sample t-test in your calculator, and when you use that 2-sample t-test in your calculator, it's going to use this formula for degrees of freedom, and it's already built in. So, good news, we don't have to really worry about that. So the t-test statistic is taking this differences in the x bars, d, subtract the differences in the mu's, which I call mu sub d, and divide by this standard deviation of the differences. And notice that does take into account both sample sizes. Alright. Quick comment about pooled versus non-pooled t-tests. There are actually two versions. If we have data from independent samples from two populations with different standard deviations, then we can use, and we must use, the non-pooled versions of the t-test, and that's the formulas that I just gave you on the previous slide. However, if we're very sure that the two populations have the same standard deviation, then we can increase the power of the test, in other words, decrease the probability of a type 2 error, by pooling the data all together to estimate the standard deviation of the differences of the means. So there's a different formula for the standard deviation if you pool them all together and figure that there's one standard deviation overall, and the degrees of freedom is a little bit different formula. In this course, we will always use a non-pooled version for this test. In your calculator, it gives you the option of choosing pooled or non-pooled, and if you're sure that your two populations have the same standard deviation, or at least you're pretty confident, then you can get a better result if you use the pooled version. However, for our class, we will assume that we do not know this information, so we will use the non-pooled versions. Okay, so when it asks you if it's pooled, always select no for this course. So let's look at an example here. A study was performed to determine differences between diastolic blood pressure reading between men and women. The following table gives summary statistics for the two groups of subjects. We have the females, we had 13 of those in our test, had a mean diastolic blood pressure of 71.08 with a standard deviation of 9.22. The 16 males had a mean of 77.37 and a standard deviation of 8.35. Notice these are definitely independent. We don't have the same subjects, no overlap. Nothing should necessarily be making these dependent. Okay, especially if they're just randomly selected. in each case. So, we have independent samples. Is there sufficient evidence at the alpha equals 0.05 level to determine that there is a difference in the diastolic blood pressure reading between men and women based on this particular sample? And also compute a 95% confidence interval for the difference in diastolic blood pressure. For this one, we'll use females minus males. So since we're doing females minus males, we will consider females data set 1, males data set 2. So, the good news, again, this is built in a calculator, so it's really quite easy to perform the test. We just use two sample t-tests, so we go to stat, left arrow to test, go arrow down until you get to two sample t-tests, choose that. In this case, we already have the summary statistics computed for us, so we choose stats for the input and type in. For data set 1, the mean was 71.08. So X bar 1, the sample mean of data set 1, is for females. Females are 1, males are 2 in this particular example. So 71.08. Standard deviation 9.22. N sample size 13. And then type in the same data for the males in the next 3 lines. And then, of course, you see a little arrow in the lower left corner there of the screen. So you down arrow. Here we go. Down arrow. And you're going to have some things to choose. So this one we're just seeing if there's any difference. So we want to go not equal to. So it's a two-tailed test. Pooled, always no for our class. There's no reason to believe that the standard deviations are the same for these two groups. In fact, the sample standard deviations are definitely different. And then do a calculate. Or you can draw it as well, but I'm going to do a calculate. It returns a t statistic, negative 1.905, etc. A p-value, 0.068, so about 0.068 whatever. And degrees of freedom, based on that calculation we did before, showed earlier, 24.58 something. And it also returns some summary statistics, X bar 1, X bar 2, down arrow, and so forth. Now these should have been the things that we actually typed in. But if we do this not from statistics, but from our data list, and we have a list 1 and list 2, and then run this, this will be useful information for us to have, because it will be the summary statistics for those two lists of data. The main thing we need right here is the p-value. So 0.068, and we notice that that's greater than 0.05, so what's the conclusion? Well, if p is greater than alpha, remember the conclusion is we do not have sufficient evidence to reject the null hypothesis, so we accept it. So there is not sufficient evidence to show that there is a difference between diastolic blood pressure of men and women based on this data set and at this alpha level. Now, of course, if we'd chosen a different alpha level, we might have got a different conclusion. For example, an alpha level of 0.1, we would have had p less than alpha, and we would have reached the conclusion that there is a significant difference at that level of significance. And we want to find a confidence interval for the difference. We choose a two-sample t-interval. So look at this series of screens at the bottom. Again, we go to stat and test and just find the two-sample t-interval. We may have to down arrow a little bit, but we'll find it. We choose it from statistics. In fact, they're already typed in if we've done this other one up here. Again, it's not pooled, and we calculate it. Same degrees of freedom, and everything's the same as before on the statistics. This one gives us the interval of negative 13.09 to positive 0.51. And no real surprise, notice 0 is actually in that interval and includes some positives and negatives. So it could be that we're 95% confident that the difference is somewhere in there based on this. But notice that that does include 0, so there's a good chance that this was not a significance. However, you should not really use the t-interval to determine the test. The test should be from the t-test, the two-sample t-test in this case. Let's do another example. Selling prices of several homes were taken in 2 suburbs of Rochester, New York, as given in the table to the right at a particular time, over a particular month or something. Is there sufficient evidence at the alpha equals 0.05 level to determine that the selling price of homes in Perrington was higher than in Penfield at this particular time? Now, you've seen enough of this. You should be able to go ahead and finish this yourself. Now, let's think about it a minute. These are independent samples, okay, and we can put these in our calculator. We do not know the population standard deviation, so this is going to be a t-test rather than a z-test, and we are testing for the mean level. So that is a 2-sample t-test. Go ahead and put this in your calculator now and see if you can work this out and check it against the next screen. Press pause now. Well, this is the data that I've typed in my calculator here. So I start by going to Stat, Edit, and clear List 1 and clear List 2, and type in these values from Penfield in List 1 and Perrington in List 2. And if we do a 2-sample t-test, we go down and we choose Data, because this is coming from our data list, from one of our lists, 2 of our lists. List 1 is L1 and List 2 is L2, both for frequency 1. And we want to test Penfield higher than Perrington higher than Penfield is our alternative hypothesis. Now Perrington was List 2, so we want List 1, mu1 less than mu2. So we choose less than mu2. Not pooled. Go down just one more arrow and it says calculate. So calculate, and we get this. So we're testing alternative hypothesis of mu1 less than mu2. The null hypothesis is that the means are the same. We get a t-value of -1.4 and a p-value of 0.09. What's our alpha level? 0.1. P is less than alpha. What's the conclusion? Alright, the p is less than alpha. We reject the null hypothesis in favor of the alternative. So with a p-value of 0.09, there is sufficient evidence at the alpha equals 0.1 level to say that the selling price of homes in Perrington was higher than in Penfield at this particular time. Notice that it also gave us our summary statistics. So the average value in Penfield is $170,147, and in the average value in Perrington is $224,771. Standard deviation in Penfield is $55,644, and the standard deviation in Perrington is $109,650. And both had 10 homes selected for the sample. We could do a confidence interval for the differences as well. Okay, that gives us an overview of 2-sample tests for t-test, mainly for t-test. The z-test would work the same thing, but you would have to know the population standard deviations of both populations.